We're going to begin a discussion of acoustics and perception. These are very different subjects, acoustics being the subject of the physics of sound, and perception being the subject of our sensing of sound and our cognitive processing of sound. And so while these are very different, they are both sort of our links between the imaginary abstract world of computer sound generation and the real world of actually the physical world and our world of experience. Sound is vibration or air pressure fluctuations. We can hear about 0.001 pounds per square inch for a loud sound, and I'm purposefully using English units of pounds and inches because I think if you inflate a bicycle tire or check the tires on an automobile, you might have some sense of what that means, whereas pascals, to many of us, are pretty abstract terms. Anyway, the sea level air pressure is 14.7 pounds per square inch, just to give you a reference there. Cabin pressure in an airplane is about 11.5 pounds per square inch. So 0.001 is a tiny, tiny fraction of kind of the nominal pressure. The air pressure fluctuations deflect our eardrum, and the amount of deflection is about the diameter of a hydrogen atom at the threshold of hearing. So we have extremely, extremely sensitive ears and hearing apparatus. What can we hear? The range of frequencies that we hear is from about 20 hertz to 20 kilohertz, so 3 orders of magnitude. Although realistically, as we grow older and as we're exposed to loud sounds, which affects most of us, our high frequency hearing is impaired, and so the range is typically less than that. Speaking of loud sounds, our range of hearing is, in terms of loudness, is about 120 decibels. That's measured from the threshold of hearing at the frequencies we are most sensitive to up to the threshold of pain or discomfort from loud sounds. In practical terms, the dynamic range, this 120 dB range, is actually limited because there's so much background noise that the noise masks the quietest sounds that we can actually hear. So if you want to stop this lecture, you will probably hear some combination of computer fans, ventilation noise, street noise, other environmental sounds. And so that's frequency and amplitude. And we are also, of course, very sensitive to amplitude spectrum. So this little diagram on the right sort of shows in a spectral view our range of frequencies, our range of amplitude, and the idea that the shape of the spectrum is something that we are very sensitive to. Real-world sounds are complex. You know, we've been looking at a lot of synthesis algorithms that tend to produce very clean, simple, specific spectra and waveforms. These are not really characteristic of the real world, and it's important to know that because if you want to synthesize rich musical sounds that are pleasing to the ear, it's good to know that real-world sounds are not simple sinusoids, they do not have simple constant amplitude, and so on. So here are some examples of just kind of general sound categories out there. Noisy sounds, like if I make the sound shh, that's a noisy sound. They tend to be broadband, meaning they contain energy at almost all frequencies, and the amount of energy at any one frequency or the amplitude at any particular sample is random. So the overall spectrum looks kind of like this. Percussion sounds, on the other hand, thumps, bell clangs, pings, knocks, tend to have resonances. So the energy is more concentrated, but there are often many resonances or many vibrations that are exponentially dying away. And so a typical spectrum might look something like this. Here you see resonances at these different points. The fact that each vibration decays in general exponentially results in some widening of that peak. The faster the decay, the wider the peak, and generally the shorter the peak. Other sounds, pitched sounds, which we often call tones, tend to have harmonically related sinusoids. In fact, I think we know from previous presentations that if the signal is purely periodic, then mathematically it does have harmonically related sinusoids. It can be decomposed into the sum of sinusoids that are all multiples of some fundamental frequency. So we get harmonically related sinusoids. In physics, this periodicity is characteristic of some kind of mechanical oscillator that's driven by an outside energy source. So if you're bowing a string, or you're singing a tone, or you're blowing into a clarinet and that has a vibrating reed, all of those are instances of driving the oscillator with a more or less constant source of energy. And in those cases, almost invariably, you end up with the oscillating system falling into a periodic stable oscillation, which, as again, we know mathematically that if you have a repeating periodic oscillation, you will have harmonic partials. On the other hand, we have tones like piano tones and some other percussion instruments, vibraphone, where you hit a bar or you hit a string and it vibrates, and it does produce a tone, but these are sort of special cases of percussion sounds that have approximately harmonic partials, but because the instrument is struck, there's no driving energy input to force the result into a periodic signal. And so just like percussion sounds, you get exponentially decaying sinusoids. They may be approximately harmonic or very harmonic like in a piano, but not precisely so.